electronic structure calculations. But I will try to talk about band structures, at least at the end, maybe if there's time. But even so, I tend to focus on methods and reasons for making decisions in your algorithm design. And so I might forget to present the results later. So I'm going to throw them on the screen now. So you see band structure on the screen. They're the same band structure on the left and the right. This is just a fake material that I made up. It's a simple cubic lattice using a tight binding model for hydrogen-like orbitals on each nuclear center. The band structure in the middle of the screen gives the analytic results, and also the orange diamonds tell you how my algorithm performs under ideal conditions. On the right, you see the algorithm performing under experimental conditions. And you can see that the experimental conditions are quite a bit messier. We will return to this plot several times throughout the talk, and I will point out to you various things to look for in the talk. But for now, let's move on. I want to paint a little bit of context this talk, because quantum computing can mean a lot of things, especially if you pay attention to the media. You might have one idea when I mean another idea. So first of all, what problem is it that we're solving? We're using a quantum computer to solve an electronic structure problem. So we're developing an algorithm to implement on a quantum computer. So you might compare this to probably the most popular sort of quantum algorithm out there in the world, which is Peter Shor's integer factoring algorithm, where you should be able to factor a very, very, very large integer, find all its prime factors exponentially faster than the algorithms you learned in grade school. And the reason this one is so well known is because it has huge, huge implications for how we use the internet today. Our secure communications, the whole HTTPS protocol, is built around the idea that factoring integers is very hard. And so if Shor's algorithm is, if somebody can make a quantum computer to reliably implement Shor's algorithm, then all that we have on the internet sort of falls apart in some way. I do not know if the algorithm to solve electronic structures in full configuration interaction with as much accuracy and efficiency as we can do band structures today. I do not know if that will have as direct a societal impact, but that is the idea, that is the hope, and that's why we're all here. I also want to contrast on this slide another reason that material science and quantum computers interact, and that is to do electronic structure calculations to design or to build quantum computers. This is a very active area of research and also a very, very important one, but it's also one that I personally have absolutely nothing to do with. So we're on the algorithm design side as opposed to the building quantum computers side. And finally, one last contextual thing. I trust that just about everybody here understands and knows band structures quite a lot better than I do. But in case you need a reminder, I'm talking about solving Schrodinger's equation for a single electron in a periodic potential. The most famous example of a band structure is probably silicon, which has the nice band gap right in between the valence and conduction bands. And that tells you that silicon can be a good semiconductor, and that's how it lays the foundation for all of our digital age. Another thing that we need to contrast that you might have heard in the literature is there's actually different models of quantum computation. So for example, I'm working with gate model quantum computing. You might also have heard of something called adiabatic quantum computing. The main difference here that I'm concerned about is the fact that adiabatic quantum computers have that we have today, that are functioning in use today, they have on the order of thousands of qubits. Whereas the hardware that I have available to implement my algorithms has on the order of a dozen. A couple of companies are pushing into the hundreds just in the past year, but there's still an order of magnitude difference here. The thing to bear in mind is that the problems that each of these models addresses, the algorithms that you can implement, are completely different in either one. And it does not mean just because adiabatic quantum computers have 10 or 100 times more qubits, it does not mean that they're more powerful. It just opens up different algorithms that you can solve. And finally, the last point that I want to emphasize is that quantum computing is still in the area of basic research. Useful applications are probably a long way off. Perhaps the talk after mine will attempt to argue something different, and I'm looking forward to that. But for now, I would temper your expectations. I raise this because you may have heard a few years ago, Google announced that they had attained what they called quantum supremacy, which is to say that they have done some computation on their quantum computer, which would take a classical computer thousands of years to emulate. And that's a really important step for our field. It's really important to be able to claim this thing, but there's a couple of caveats with this claim that I want to point out, which is, first of all, within a few months, IBM published their own paper claiming to have done that classical computation that would take thousands of years in a few months. And second, the computation that Google did, it demonstrated the ability to generate quantum states that would be, in principle, difficult to emulate classically, but it did not do anything useful with it. It wasn't implementing any algorithm. It was simply generating the state and then collapsing it, measuring it. And that's no fault of Google's. This is just, we're taking footsteps along the path to some real quantum advantage. And it is a long road, mostly for a number of engineering challenges. It's very difficult to implement a physical qubit that is able to respond the way that we want to when we want to drive its system forward, but also remain resistant to interactions with the environment that can decohere and destroy the information that we're putting into it. So we're still in the area, the era of noisy intermediate scale quantum computing. And so here I have put my results back on the screen. I want to draw your attention to the experimental data on the right. If you can find the red squares and the purple diamonds, those are results executed on 2 of IBM's smaller computers. So that's real quantum data that you're looking at the screen there. And if you can't find the dots, you can probably find them as far from the correct bands as possible. Well, some of them aren't so bad, but the point is that noise has a very deleterious impact upon the calculation still. And so once again, temper the expectations. Okay, now I'm going to go into a little bit of a overview of how quantum and classical computing differ from one another, and I'm going to be leading up to being able to explain the variational quantum eigensolver. That'll be the most important part of this talk. So in the meantime, first of all, what's the first thing that you think of when you think of quantum versus classical? Well, some people say that quantum computers are so powerful because as you add each qubit, the number of states that you can explore expands exponentially. And that is true, but it's also true of classical computing. 1 bit gives you 2 states, 2 gives you 4, 3 gives you 8, and so on. The distinction between classical and quantum computing is rather that the quantum computational state is a vector in that exponentially dimensioned Hilbert space. So it's forming a continuous space as opposed to the classical states, which are just these discrete values of 0 and 1. And that has a big impact on how we think about programming the quantum computer. When you think of classical computer programming, you probably first think of things like Python or C, these high-level programming languages. But we have many levels of thinking about classical computation. The most useful one, especially for the gate model quantum computing, is these logical circuits. That's the picture in the middle here. With the NOT gates and the AND gates and the XOR gates that take in information as wires and then output some transformed value. So that's the idea. You are taking in some information in the gate, and then you output a transformed version of the information. Now we can think of the same exact thing in the quantum circuits. I'm afraid the picture is smaller than I realized, so you can't probably see anything. But the main difference here is that instead of these logical Boolean gates, which have there's only so many discrete states that they can take in and put out. When you have a quantum computational state, which has a continuous, each quantum state can take a continuous value, that means that the instruction set, the type of gates that you can put in your quantum computer are, it's a much richer, more diverse set. And that is how we are able to get a more powerful computer that's able to do more things in some contexts. The last thing that I want to comment on here, which I think is very helpful to understanding really what's going on in the quantum computer, is that both of these circuit diagrams are just one level removed from the physical implementation of how a computer really works. But in the classical logic circuit, that diagram of wires and gates, it maps pretty much directly onto the actual physical circuitry of wires and transistors that you see in a microchip. Whereas in the quantum circuit, we don't have a spatial correspondence, but a temporal correspondence. And that means that we are using usually something like microwave pulses to drive our qubit system forward in time along the quantum circuit. So that I think that's just a helpful idea of really visualizing what the quantum computer is doing on the inside. It's a temporal analogy to the unitary operations that you're doing. And then finally, the last thing on quantum versus classical computing is the very well-known measurement problem. Extracting information from the quantum states is going to require measuring it, and measuring the quantum states is going to require destroying some information. And in fact, it's also going to be probabilistic. We don't know a priori which classical state a quantum state collapses to when you measure it. And the biggest significance of this is that in almost every quantum algorithm that you'll find, there is some part where you have to reset the quantum computer and then repeat the same quantum circuit execution and redo your measurement. And the idea is that you're collecting statistics on the quantum states that you are preparing. So bring the results back up the screen. If you can see now in the experimental data, there are some very gray dots. Oh, that's hard to do with lag. All right, yes, so gray dots right here. These are individual trial runs, not on a real quantum computer, but simulated on a classical computer as though it were a quantum computer. So it's behaving in the same stochastic way. It just doesn't have the efficiency of quantum computing. But you can see there's a huge variance in all those gray dots. And when you take into account all of them and you calculate the median, that's the green asterisk, when you take into account all the dots, you get acceptable results, but each individual trial, because it's very probabilistic, doesn't tell you a whole lot. Okay, now in the next part of the talk, I will be describing the variational quantum eigensolver. This is one of the more popular algorithms to use for quantum chemistry, so solving electronic structure calculations. It is far from the only one, and it is probably not the best one, but it is the one that I'm using. And in fact, most of you are probably already familiar with almost all the details here, because it's basically just the variational method to solve Schrödinger's equation. So the objective is to find the eigenstates and eigenenergies of a Hamiltonian, and we basically proceed by asserting that the wave function fits some functional form that has some parameterization. And then we just find the parameterization that results in the smallest energy. And that guarantees, like under the variational principle, that guarantees that the state that we found is a good approximation of the ground state of the system. And in fact, if our ansatz, that functional form, is sufficiently expressive, then it may indeed be precisely the ground state. And then we can also find higher states than the ground state by taking advantage of the fact that any eigenbasis is going to be an orthogonal basis. And so all the eigenstates are orthogonal to the ground state. And so if we just add in the additional constraint to our ansatz, not only does it have to satisfy some particular functional form, but it also has to be orthogonal to the ground state, then we can repeat the variation and obtain the first excited state, and then do it again to get each excited state that we care about. Now, to adapt this to the quantum computer, the main point is probably number 2. We have to map a physical wave function. So, for example, in the band structure problem, we're talking about a single electron wave function in the presence of a periodic potential. We're mapping that spatial wave function somehow onto the computational states in our computer. And then we're going to have some process to measure the expectation value of that of the Hamiltonian of our system with respect to this computational state that we've prepared. And that is going to give us a cost function that we can then optimize, tweak the parameters until we find a minimum, and then we quote that as our ground state. So the problems we have to think about when solving this on the quantum computer are one, how do we actually do this mapping of spatial electron wave functions onto a computational state? 2, how do we change the Hamiltonian that we need to take the expectation value of to get the energy? How do we take this Hamiltonian and map it onto a set of qubit operators? Qubit operators are usually the Pauli spin operators acting on each qubit. So for example, there might be a sigma x operating on qubit 1 and a sigma z operating on qubit 2, and so on. And there's all those combinations of all possible x, y, and z on each qubit. We need to somehow map our Hamiltonian onto an operator like that. And then finally, we need to have some quantum circuit that prepares a computational state corresponding to a physical state, prepares a computational state in a parameterized way. And that will let us tweak the quantum circuit until we find an energy that gives the minimum. And there's a few other things also, the actual details of how to calculate the expectation value, how to enforce orthogonality in your quantum circuit, and an intelligent way of actually deciding how to vary the parameters so that you are efficiently finding the minimum. I'm not going to go into those in any more detail, but beware that all 3 of those are their own huge fields of the quantum computing literature today. Okay, now in this last part of my talk, can I get a hint on how long I have? 10 minutes, thank you. In this last part of my talk, I will try to go into a bit more detail with band theory itself, make sure that we're all on the same page on what it is, how it works, how it relates to VQE, and on some of those points that I had in the previous slide. So here we're taking it as an example, this fake material that's a simple cubic lattice, basically hydrogen-like orbitals on each nuclear center. So the s orbital is the sphere and the p orbitals are the lobes. We expand our system in this basis. And so we're able to write out our Hamiltonian not in the usual differential form that you might see when solving the Schrodinger's equation for a finite or an infinite well, but we will use the second quantization approach using the ladder operators, creation and annihilation operators, which you will probably have seen in your solving the harmonic potential, the quadratic potential. And turns out that you can adapt those creation and annihilation operators to any system at all. And it turns out to be very useful. And I think we even saw it a couple of times in the previous talks. And so all we need in order to generate our Hamiltonian is these hopping parameters. So the A's are our creation and annihilation operators, and the subscripts nu and alpha or beta, those are telling you which unit cell and which type of orbital, S or P, that we're talking about. And then the T's are the hopping parameters, which give the energy relating, how much energy does it take to move an electron from one orbital to another. And you can obtain those T's by doing an integral calculation, or you could obtain them empirically, or you could make them up like I did. This is the advantage of the tight binding model, is that you can do theory without necessarily having to know about real materials. Okay, and so this sum in the direct space, we're summing over all the hopping parameters for every pair of orbitals in an ostensibly infinite crystal. So that's obviously not very easy to work with. So we will do a Fourier transformation into reciprocal space. So we're working no longer with the index of a unit cell, but with the momentum or the periodicity of our basis functions. And essentially what this means is we're no longer working with s orbitals and p orbitals, but with periodic versions of s orbitals and p orbitals that are the same amplitude at each point in space, but varying by a different phase. And the most important thing that we find when we do the transformation into reciprocal space is that the sum becomes a bit easier. We've now actually found that we only need to sum over 3 indices as opposed to 4. So this inner sum, it actually forms its own independent block. It's like the difference between having a million by million matrix and a 100,000 10 by 10 matrices. And in fact, that is basically what we have. We can now diagonalize each 10 by 10 matrix alone, solve the eigenvalue problem for each separable momentum. And those become the points on our band structure. So which momentum, which K value we're talking about determines where on the x-axis of the band structure we are. And then the eigenvalues of each block are the values of the energy at each band. To be clear, classically, you would do all these things still. And well, diagonalizing the 10 by 10 matrix is just doing some linear algebra to diagonalize the 10 by 10 matrix. It's very easy to do, but the point of this is to do it on the quantum computer. And so the next step is to map the Hamiltonian and the computational states. So because we are working in this separable space, with our example, we only have the 4 orbitals for each momentum. Like for a fixed momentum, we only have to worry about 4 orbitals at a time, and you can still call them S and P orbitals. So I'm just showing 2 different ways of mapping the basis orbitals, S and P, onto the computational states. And of course, what we want to do is to find a quantum state, which is a linear combination of these orbitals that gives us the eigenenergies. But the mapping between basis element to basis element is going to be 1-to-1. But here's the important point. There's more than one way of doing this mapping. And usually the decision-making that you have to do is to balance the number of qubits or the size of the quantum computer that you want to use with the complexity of the qubit operator that your Hamiltonian ends up mapping onto. So for example, intuitively, we have 4 basis states, so we should only need 2 qubits, right? 2 qubits should be enough to handle the exponential number 4 basis states. And so you can certainly do that mapping, and you can certainly take that over to map the Hamiltonian, your second quantized Hamiltonian operator. There's you just have to do the algebra to figure out what all those correspondences are, figure out which Pauli operators are corresponding to what their weights are. You can do that, but it turns out that you're going to wind up with a very dense operator. You're going to end up needing a coefficient for just about every single one of the possible qubit operators. Whereas if you add on a few more qubits, if you let yourself use 1 qubit for each basis orbital, that actually lets you generate a much sparser Hamiltonian operator when you map it into a qubit. And that means that it's going to be easier to do the operator estimation, calculate the expectation values down the line. And since that's the most important part of the quantum computing, in this case, it's probably advantageous to use 4 qubits instead of 2. And the final slide with content in it is talking about how do we decide how to develop this quantum circuit. So we have, again, 2 options, and this is, again, just 2 out of many options. I'm not even going into the most popular for VQE, which is based on the unitary coupled cluster ansatz. But this one just talks about symmetry preserving and hardware efficient. The difference here is that the symmetry preserving ansatz, it takes pains to ensure that that you never leave the active space. That is, I have decomposed my system in terms of just here. I'll go back for a second into just these there. Just these 4 basis elements. So any computational state that dips into something else that involves the 0000 basis element, or any basis element that has more than 1 activated, any computational state that has a superposition including any of those is beyond my active space. So the symmetry preserving ansatz, it just takes pains to ensure that I never leave that active space. And so it's helpful for making sure that your results are physical. Then again, it may be that it's easier to implement on the quantum computer some fixed alternating layer of single qubit gates, which are very easy to implement, and then entangling layers that might mix up the qubits depending on how your quantum computer is laid out. The important thing to realize here is that you want to balance the expressiveness and the robustness of your quantum circuit with the depth of your circuit. The advantage to the hardware efficient ansatz is that you can very easily control its depth. Depth is important because the longer the circuit is, the more likely the qubit is to decay, decohere, lose its information with the environment. And so these are the trade-offs that you have to consider when designing quantum circuits. So we'll go back to my results one last time. I hope that you have at least a decent idea of how one goes about generating the quantum results for these band structures. And I hope that you realize it's not nearly as easy as we'd like it to be. And we'll look forward to the next talk to hear about alternate solutions.
Thanks so much for this great talk and for keeping time. Questions?
Hi, very interesting talk. I was wondering, for quantum computation or quantum information processing, there are well-known mapping like Jordan-Wigner transformation,
Yes.
Perotti transformation. Which one did you use?
Yeah, here, the standard-ish mapping, it's essentially Jordan-Wigner. I do like Jordan-Wigner. It's the most straightforward, the most intuitive. What Jordan-Wigner does that I'm not doing here is enforces the fermionic anti-symmetry of electrons. So it actually makes the Hamiltonian a little bit more dense in the proper Jordan-Wigner transformation because you have to include additional qubit operators as a string of z's after your x and the y that I'm showing here. The reason I can get away with not doing that here is because I'm only working with one electron, and so there's never any electrons to exchange with, and so the z's turn out to be irrelevant there. It's a great question.
One more, if I can. So the answer selection is probably is kind of an art, right? In quantum computation. So when you started this work, how did you select? Like there are like SU2 circuits answers, and there are many answers. So how did you select this one particularly?
Yeah. Like the question is, how do you go about deciding from the whole literature what to start with? Am I understanding that right?
Yeah, that's right.
Yeah. Personally, I am a big fan of symmetry preservation. I think I'm no expert, but it just makes sense to me to want to guarantee that your result is physical from the beginning. And it turns out that with this symmetry preserving ansatz, it is very easy to do what I alluded to earlier, enforcing orthogonality in when you're finding excited states. It turns out that's very easy to do with this ansatz. And so it's the one I intuited first and also the one I ended up sticking with. But yeah, it's an adventure in the literature.
Maybe one more question.
Yes, so thanks also for the nice talk. You talked a bit about like the compactness of the basis, right?
Mm-hmm.
Did you compare, like, let's say, if you try to use a more compact basis, how much noise you maybe get in there or something like this? Because it might be for bigger problems, we hit like very quickly the limit of how many qubits we have, right? So it might be important to see how this performs.
Yeah, that's an excellent question. I'm afraid the answer is no. I haven't done much by way of benchmarking how noise scales with the various methods, but it's definitely something that should be done and should be done thoroughly. That's a very important question.
Thanks.
Then I think we move on and let's thank the speaker again. from Columbia University, and will continue the quantum computers. He will talk about a good use of quantum computers in quantum Monte Carlo simulations of molecules and solids. Take it away.
Good afternoon, everybody. And I would like to first thank the organizers for inviting me here. And thank you everybody on Zoom, and thank you everybody here for attending this talk. I'm currently a postdoc at Reichman's lab at Columbia University, and also a visiting faculty researcher at Google's Quantum AI team. So this talk is gonna be mainly about a recent paper that we had in Nature, which is about how can one unbiased fermionic quantum Monte Carlo calculations using a little bit of quantum computing tools. Before I go on with the details of this work, I'm a electronic structure theorist, and there is no better slide than our slide on electron correlation problems to start with. So let me tell you a little bit about what I mean by electron correlation for the purpose of this talk. We define the correlation energy as everything that is not included in Hartree-Fock theory. And Hartree-Fock theory, as you all know, it's a mean field approach to the electron correlation problem. And what does it actually do? Well, it determines all kinds of interesting things. One example that I like a lot, which is shamelessly from my own work, which is on single molecular magnet, and precisely determining the spin state, ground state, spin state of this molecule is a purely electron correlation problem. It actually has 9 chromium atoms, and each chromium atom has 3 open shell electrons, and the ground state has been proposed experimentally to be a doublet ground state. So all these 27 total open shell electrons are antiferromagnetically coupled down to the doublet ground state. And this is really the hallmark of electron correlation effect that is beyond the Hartree-Fock theory. And also, electron correlation effects determine the non-covalent interactions that you can find in a lot of chemical and biologically relevant systems. So one very famous example is this benzene dimer case shown here, which is the dispersion bound complex. If you ask Hartree-Fock theory to estimate the binding energy of this benzene dimer, you would say none. You would repel each other and it would never bind. So this is a purely electron correlation driven bound complex that is dispersion bound. Another example is solid state applications that I recently got extremely interested in. Of course, the ground state, optical and transport properties of any solids are really determined by correlation effects. And in quantum chemistry, we have perhaps little too many approximate methods. Everybody has their own favorite method. I'm going to tell you a little bit about what we call bread and butter in quantum chemistry. So x-axis here is the cost, and there is a this letter, which is system size. So on the bottom left, we start from mean field theory, which has cubic cost, and this is considered to be quite cheap in this plot. On the top right, we have full configuration interaction. It's a brute force approach with the cost that is exponential scaling in system size. Its accuracy is exact within the given basis set. In the middle, this is one of my favorite wave function method, low order perturbation theory. You just take the Hartree-Fock theory as a 0th order wave function and add a little bit of electron correlation effect through perturbative expansion up to the 2nd order. And to the 5th scaling method. And then we have diagrammatic methods under the umbrella of couple cluster methods. They are formally infinite order perturbation theory. It's more expensive than MP2, but it is more accurate than MP2 in a lot of cases. The flip side of this plot is that the system size you can handle is ultimately limited by the cost you have to pay for. So if you want to do Hartree-Fock or MP2, you can study a medium-sized molecules like C60. But if you insist on the exact accuracy here, FCI, you will be limited to maybe in most 2 heavy atoms, so diatomic molecules. And throughout this talk, I'm going to talk about this great outlier here, auxiliary field quantum Monte Carlo, or AFQMC. It's a great outlier in the sense that its cost is somewhere between n to the 5th and n to the 6th. So it's more expensive than MP2, but cheaper than CCSD in an asymptotic sense. And its accuracy is surprisingly actually better than CCSD and little worse than CCSD parent T, or sometimes it could be even better. And of course, these points are actually based on empirical studies that we've performed in the past 20 years or so. And recently we conducted a benchmark study of baseless AFQMC to actually be able to put this point here with some confidence. So this is a benchmark study. The benchmark set known as W for 11, and there are lots of subsets, 5 subsets here. And what you can see here is CCSD parenthesis T, which is known as the gold standard method. This achieves less than a k-culprit deviation across the whole data set here. But if you look at AFQMC, it's a little better than CCSD, which is the green bars here, but a little worse than CCSD parenthesis T. I want to also point out another example where we did several years ago, this AFQMC versus couple cluster methods for uniform electron gas, which is a prototypical model for metallic systems. And in particular, the point here, which is the 900 or so plane waves. And if you look at these numbers, this FCI-QMC which is formally an exact number for this parameter regime, you can see that AFQMC is even more accurate, more closer to exact benchmark number than CCSD with full triples. So in some cases, we can do even better than parenthesis T, and that's why I'm particularly excited about this outlier. But for the remaining talk, I'm going to talk about how one can bring this point even upwards past the accuracy of CCSD parenthesis T, and that's what I'm going to be talking about. Before I go on, let me tell you a little bit more about what I mean by AFQMC. I believe Miguel Morales from Flatiron will be giving a talk on AFQMC tomorrow in the morning. So I'm going to keep it quite brief just within this slide. Oops. We perform imaginary time evolution. That's what AFQMC is for, and that's what all of these projector Monte Carlo methods are for. We take the Hamiltonian that we know and we exponentiate it and multiply it by minus tau, where tau is the imaginary time. And in the long tau limit, we can actually approximate the ground state up to arbitrary precision. And that's really the point of doing imaginary time evolution. But of course, if you do it as written here, its cost is actually exponential scaling in system size. But it's exact, but you're not doing any better than FCI, which like I said, it can only do maybe 2 heavy atoms at most. So you can play some tricks. You can sample the ground state through some Monte Carlo procedure. So you're going to be writing this ground state as a weighted summation over statistical sample wave function phi I here. And each of them has a specific weight WI here. If you just do this Monte Carlo sampling, it turns out AFQMC is zigzag, but it's zigzag in a very interesting way because the actual cost of doing AFQMC is still exponential scaling. Each sample doesn't cost exponential overhead, but the number of samples you would need will grow exponentially with system size for a fixed statistical error. So to be more precise, if you monitor this energy as a function of imaginary time, initially AFQMC closely follows this exact imaginary time propagation results. But after some while, as you approach the long tau limit, you actually essentially get random number in the end. Statistical uncertainty is too big that you can't really get out any statistically meaningful results in the end. So in practice, what we do in AFQMC is to impose a set of constraints based on the overlap value between your statistical sample wave function or Walker and a priori chosen trial wave function psi t. So if you have a good trial, meaning the quality of trial wave function is so good that it's close enough to the exact ground state, then you will be closely approximating the exact ground state in the long tau limit. But if you get unlucky and you pick a wrong trial or bad trial, you can even get a an energy that is lower than the exact ground state energy. It's a non-variational approach. So the quality of trial wave function will wholly determine the accuracy of this constrained imaginary time propagation. So the point I put here, which is a great outlier still, is the AFQMC calculations with a trial wave function that takes Hartree-Fock theory, which is the simplest possible wave function you can pick as a trial wave function. And as I said, this talk is going to be about how to move this point upward. And I'm going to be actually talking about a strategy that borrows quantum computing tools to implement more sophisticated and accurate trial wave function for AFQMC. Before I go on, I guess in the previous talk, we heard some things about why one should care about quantum computers, but let me give you a brief sense in one slide why I think we should all care about. And as you probably realize, there are too many interests in many places. As you know, industry, lots of big players are trying to build quantum computers right now. And not just the industry, it's also our government wanting to actually start national quantum initiative. And all these things are because of this notion that for certain computational tasks, there may be a good chance that quantum computers are exponentially better than classical computers for certain computational tasks. And by classical computer, I mean your laptop or desktop. And because of this notion, there would be some transformation from the classical computer to quantum computer entirely for some computational tasks. That's why we're all interested in this. Quantum computers harness quantum mechanics for computation. What does it actually mean? We learned a little bit about these quantum circuits in the previous talk. So the way it works is we initialize, so the way you read it is from left to right. You initialize your states at rest conditions. So meaning all two-level systems are in its ground state, 0, 0. And you're gonna go from left to right. And each of these boxes and letters and symbols, they are giving you a specific instruction of evolving these two-level systems in time from left to right. So if you go from left, you run into this Hadamard gate and CNOT gate, and in the end, you are getting a state that is known as the Bell state, 0, 0 plus 1, 1. And to emulate this on your laptop, you need to do some linear algebra operations whose dimension is 2 times 2, so it's 4. You can make it a little harder by adding 1 more qubit. So again, it's the same. We start from 3 0 qubits and we go from left to right. In the end, you create a state that is known as the GHZ state, the 0, 0, 0 plus 1, 1, 1. And to emulate this classically, you need to do linear algebra operations of dimension 8. You can make it a lot harder by adding n qubits, and you're going to throw in some of these T gates and Toffoli gates that will ultimately make this circuit inefficient to simulate classically. So quantum computers can efficiently contract unitary tensors. That's what it is actually for, mathematically speaking. These quantum circuits are just tensor representation. It's a matrix times a state vector, and it is actually extremely efficient at contracting these unitary tensors. All these gates are unitary. There is no efficient classical algorithm to contract these tensors, at least at the moment, and it's very unlikely there will be one. That's at least what many people in the field are thinking. And the challenges are really realizing either fault tolerance or coping with the circuit noise. Because if due to the circuit noise, what it means is from left to right, you evolve this set of n coupled qubits. In the end, you end up getting a state that you didn't desire in the beginning because of the circuit noise. So you need to really cope with the circuit noise, either remove it completely by realizing fault tolerance or somehow live with this with some clever error mitigation technique. The central question we have in the field is, the first one is, are there any chemistry relevant quantum circuits? Are these quantum circuits, these unitary circuits, any useful for doing good computational chemistry problems? are there any practical quantum advantages that are relevant for computational chemistry? I'm not the first one to ask these questions. People have been thinking a lot about these in the context of near-term quantum computational chemistry problem. And in the previous talk, we learned about this variational quantum eigensolver approach, which is really practicing the well-known variational principles in a quantum classical hybrid fashion. So the trial wave function here is a sophisticated trial wave function, something like unitary couple cluster wave function. If you recognize this, the usual couple cluster wave function would have e to the t, but the unitary version has t minus t dagger, and it's unitary, so you can write an efficient circuit representation for this wave function, unitary circuit. And what you do is you measure the energy and the gradient on the quantum computer and then do the rest of the optimization procedure on the classical computer. So this is a very simple idea that actually has been very, very popular in this field. But if you look at the literature, the largest BQE computation that's been done so far has 12 qubits total. And somewhat surprisingly, the trial wave function they used was Hartree-Fock theory. And as I said, Hartree-Fock theory has no correlation. So this is a classically tractable calculation that they actually did, even very small scale, 12 qubit. And the largest BQE computation with electron-electron correlation, as I said, this is really what we're after in quantum chemistry. And they had 6 qubits to describe 4 electrons and 4 orbitals. And these two results that I'm showing here are, these are the types of calculations that you can finish on your laptop by the end of this sentence. So it's not really an impressive achievement in the computational chemistry sense, but it is actually remarkably great that they can actually do this. Really, any useful results are considered to be heroic, because as a quantum circuit is really precisely controlling n coupled qubits from the left of the quantum circuit to the right of the quantum circuit, you need to do it in a very precise way, avoiding all these causes for circuit noise in order to produce any computationally meaningful results. So these are really the reasons why I think these results are actually heroic effort made by Google and IBM. But I'm a quantum chemist. I really like things that are practically useful. So what else can we do is the question I started to ask when I entered this field. As I said, AFQMC is all about the trial wave function, meaning the accuracy of AFQMC is wholly determined by the quality of trial wave function. If you have a good trial, you get good result. If you have a bad trial, you get a bad result. We have, unfortunately, limited choices available on the classical computer. We can really only do Hartree-Fock theory as a wave function, as a polynomial scaling trial wave function for AFQMC. Other options such as complete active space type wave functions are exponentially expensive because there are exponentially many determinants to enumerate. So if you were to also do something like unitary coupled cluster wave function as a trial wave function, the evaluation of this overlap is exponentially expensive with system size. So we are really limited to just Hartree-Fock trial wave function if you were to use the classical computer alone. Of course, the natural question is to ask, can we actually use complicated quantum circuits that go far beyond the Hartree-Fock theory, Hartree-Fock wave function as a trial wave function? And the answer to this question is yes, because quantum computers can write down a quantum circuit that involves preparation of psi trial and preparation of the statistical sample wave function phi I, and computation of this overlap can be written as a unitary quantum circuit that I talked about before. This goes under the name of Hadamard test in this field. So yes, we can compute this quantity efficiently on the quantum computer. So this really brings us to a new type of hybrid algorithm that is known as quantum classical hybrid AFQMC or QC-AFQMC. I will focus on AFQMC, but it really applies to any types of projector Monte Carlo as well. Just to give you some sense in a pictorial way, we launch quantum Monte Carlo calculation with a bunch of statistical sample wave function with all weights initiated to be carrying the same sign. And as I said, the global wave function is written as a weighted summation over statistical sample wave function. And you're going to evolve this stochastically in imaginary time from left to right. And once every in a while, you will run into negative, these weights with negative sign. And these are the samples you have to actually discard. Otherwise, there is no statistical efficiency you can gain in the end. So the way we do this is to actually evaluate the overlap between the statistical sample wave function and trial wave function. And you evaluate them by querying the quantum computer what the value should be, and the value that it measures out will be returned to the classical computer to update these weights. And if the weights flip the sign, it will actually immediately discard these samples. Of course, this procedure inherently introduces bias. As I said, bad trial wave function for A of QMC will give you bad results in the end. But as you actually increase the complexity and accuracy of psi trial towards the exact ground state, A of QMC results will also become more and more accurate and closer to the exact ground state energy. I want to emphasize that this QC-QMC or QCA of QMC has a different subroutine than variational quantum eigensolver. Our subroutine measures out the wave function overlap value, whereas variational quantum eigensolver measures out the energy and associated with gradients with respect to the wave function parameter theta. We implement this idea on Google Sycamore processor. We want to estimate psi trial overlapping with phi every time step for every single statistical sample. This is actually a quite scary demand for near-term quantum computers. We simply can't call the subroutines too many times. What we ended up doing, which was Bill Huggins, my close collaborator's idea, is to use this technique known as shadow tomography once initially before running the actual quantum Monte Carlo simulation to map out the trial wave function. So what does it actually do? Well, in shadow tomography, we start by defining a quantum channel M here. So rho here is a density operator. It's a ket of psi, bra of psi. So it's ket bra. It's a density operator of a state. We have this state, and we're going to apply this quantum channel. And what it does is we're going to draw some random unitary operators U here from an n-qubit Clifford group. So this is this contains a group of unitary operators, and we're going to randomly draw a member from that group, and we're going to statistically average this procedure over n sample. And each of these Clifford unitary randomly chosen ones, we're going to apply them to rho. So we're going to actually contract the unitary tensor with the state vector we prepare. And then we're going to measure in the computational basis, meaning that individual qubits will be read off in the end, ones or zeros. We're going to repeat this n samples times, and that's what I'm going to be calling quantum channel measurement for the state rho. What happens is, in this particular case where we draw unitary operators from the n Clifford group, we can invert this channel analytically very efficiently because we don't even have to actually invert this at all in the end, which is that if you apply M inverse to M of rho, you get something just in terms of M of rho, and thereby we can obtain an approximate representation for the state rho we wanted to actually know. They can only be prepared efficiently on the quantum computer, but we have some classical representation of M of rho, which I will call classical shadows. So just to repeat what I said, this is really what happens in my quantum circuit that ran on the Sycamore quantum processor. We prepare this state, and this state happens to be a linear combination of vacuum, which doesn't contain any electrons at all, and psi trial wave function. And then we're gonna apply this quantum channel Clifford measurements. I call it measurement because we're gonna be reading off the computational basis elements in the end. And once we do that, we can do classical post-processing, meaning only up to this point, the quantum computers are doing the work. But after this point, the classical post-processing happens on the classical computer in a very efficient way. And using this row shadow, essentially just M of row, this Clifford measurement results, we can efficiently estimate the psi trial overlap with phi, the statistical sample wave function. And it works for any psi trial you can write as a quantum circuit. And that's really the point of this exercise. So the measurement cost here goes like log of M divided by epsilon square. M is the number of statistical samples in the simulation. And 1 over epsilon square is the adder in this overlap estimation. So we can estimate this up to the additive adder epsilon efficiently. We want to treat many electrons and orbitals to be competitive with classical methods. We don't want to be running calculations that can be done on your laptop by the end of this sentence anymore. So we want to really make sure that we can do lots of electrons and orbitals. Classical AFQMC can scale up to 2,000 orbitals that would correspond to 4,000 qubits, which we can't really afford to do at the moment. So we have this technique known as virtual correlation technique, which allows for a lot more orbitals and electrons at no additional measurement overhead. So in the usual quantum chemistry jargon, we would do an active space calculation on the quantum computer. And that information alone is enough to run the AFQMC calculations on the whole space, not just the active space. So this technique is useful because we can do 8-qubit quantum computation to compute the correlation energy for 120 orbitals. We can do the same for 12-qubit and 16-qubit. And these are the 3 examples that I will discuss now. The first example is H4, which involves only 8 qubits. It's a square geometry at 1.23 angstrom. This is my favorite strong correlation problem. The reason for that is that it really has 2 quasi-degenerate Hartree-Fock determinants. So if you were to apply mean field theory or any low-order perturbation theory on top, it will all miserably fail for this problem. It's cooked up in a way that any mean field approaches would actually grossly fail. My quantum trial has perfect pairing wave function. It's a jargon in our field. It doesn't matter if you understand this part. What's really important here is this quantum trial has an efficient representation on the quantum computer, not on the classical computer. And it goes far beyond the usual Hartree-Fock trial wave function that we do in AFQMC. This is already larger than the largest correlated BQE computation, which I said it involves 6 qubits. So it's already more than 6 qubits. And this is a quick look at the quantum circuit that we run, which actually starts with GHZ prep, which just creates a linear combination of vacuum state and N electron state. And then we're going to implement the psi trial. We're going to apply these random Cliffords, and we're going to measure off individual qubits, as I explained before. So let's look at some chemical reaction, atomization energy. I feel bad about calling this chemical reaction, but I really mean that it's an energy difference calculation. So H4, all 4 atoms are pulled apart all the way to the infinity. So the x-axis here is the number of measurements, it's the Clifford measurements. As I said, the quantum computers have to measure over and over again in order to obtain a classical shadow of the state we want to implement. Y-axis is atomization energy, so we should see some convergence as we improve the classical representation of the psi trial through the shadow tomography procedure. These 2 are really the experimental data. We ran it on a different day, different weather, just to make sure that these are reproducible. If you didn't have any circuit noise at all, this quantum trial ideal is at around 45 kcal per mole. And if you see the exact answer, which is at around 70 kcal per mole, and the chemical accuracy window is very, very tiny on this energy scale. If you run without any circuit noise, you're already 25 kcal per mole away. And then the actual device implements something even more terrible than this. So this is really not useful at all for computational chemistry, just this trial wave function alone. But once you combine this within this QC of QMC, we're going to use this trial wave function to improve the A of QMC calculation, then we both runs actually achieve chemical accuracy with the number of measurements above 1 million. So this is a remarkable result. And of course, you may think that this is such a trivial test. There are only 4 hydrogen atoms. So I completely agree with you, because we can compute the exact answer, not with your laptop. You need to work a little harder to get this number, but you can still get this. It's not trivial in the following sense. So if you do A of QMC with Hartree-Fock trial or CCST parenthesis T, which, as I said, it's a gold standard method in quantum chemistry, you get an error that is above the chemical accuracy. So 1.9 kcal per mole error for A of QMC and 1.4 kcal per mole error for CCST parent T. Quantum trial on the device itself is completely inaccurate, but once you combine this in this QCA of QMC, then you achieve chemical accuracy. So while the test itself seems trivial, but there is some non-trivial aspect like this is there. So this really demonstrates that QCA of QMC can work well on a noisy quantum computer. We did the same test for triple bond N2 bond breaking example, which is a classic example for a strong correlation. We have 14 electrons and 60 orbitals. It's just to make sure that this approach is a scalable approach. The purple data points in this error inset, you can actually see that we do end up getting some points within chemical accuracy, and clearly better than the red data points CCST parent T or the classical, the A of QMC calculations with Hartree-Fock trial wave function. We did the same for diamond cold curve. It's the 111 unicell, completely a toy problem. We just did it for the purpose of demonstration. And this is currently the largest electron correlation calculation on a quantum computer that is already competitive with CCST parenthesis T, which is the gold standard method that we have in our field. And this is really an improvement beyond variational quantum eigensolver. Let me end this talk by giving you some prospects on practical quantum advantages. I don't really care how things scale in some sense, because the only thing I care is end-to-end runtime to be shorter. Just with the access to the quantum computer, that's all I really care as a practical person. So I'm going to refer this to as practical quantum advantages. There is a subtle scaling issue that I didn't really tell you, which is that the quantum computers can estimate these overlap values up to an additive adder. I didn't emphasize this enough before. This epsilon is added to the quantity that you want to actually estimate. And this epsilon requires 1/√n measurements. So if you have to refine this quantity more and more, you have to measure more and more. Unfortunately, these local quantities decay to 0 exponentially with system size. So at some point, you will have to work exponentially harder on the quantum computer to resolve these small quantities. This could be a very concerning measurement overhead. But we have a supplementary section F in the paper talks about these issues. But I believe this really doesn't make this approach not useful in the sense that it's possible that this overhead of measurement is not the bottleneck for some systems. It was clearly not the bottleneck for the systems we looked at. We have to continue to identify such systems. One can also postpone the decay of these local quantities by using Walker wave functions that take a form of unitary couple cluster or matrix product states, just not single Slater determinant. And really, I want to emphasize that we need an algorithm that gives us a better end-to-end runtime for practical quantum advantages. With that, I will conclude. I talked about this new approach for near-term quantum computation. And I showed by examples that it is more scalable than BQE. We need to really continuously identify interesting systems to demonstrate practical quantum advantages, and many extensions and improvements to come in the future. We'd like to thank my advisor, Dave Reichman, and other collaborators, especially Bill Huggins. And thank you very much for all of you for your attention.
Thanks so much for this very interesting talk. Maybe we take like 2 or 3 questions, and then we have actually a break after, so you can keep asking questions after closing the session. Saurabh, maybe first.
Thanks. So, I mean, regarding your practical concern, which is very important, can you give us a feeling like for you doing these calculations, like how hard is it? How easy is it to access this computer? How long does it take to run? I mean, I realize it's very problem and system dependent, but
Yeah. Are you asking how hard it was to run things that I presented today? These actual examples.
right.
So there is a sociological bottleneck in this procedure because I don't personally have access to the actual hardware. So I had to ask Charles Mayo, who is on the quantum AI team. I would email him this quantum circuit. He needs to find the time he can actually focus on this project. He would run them and report back to me. So there is an overhead because of Charles' availability, but there can be some days, but the actual quantum computer time, GPU time for this example, I believe was 4 hours. And the actual AFQMC CPU hours was a lot more. So it's clearly not the bottleneck at the moment. And the question really is, can we find an example like this at the scale that is not easily classically, there is no classical method that can easily do an accurate calculation for. So that would be something around 50 orbitals and 50 electrons. And this is something we need to continue to try hard. But the actual device we have right now has, I think, 72 qubits, at least in Google. And that is certainly may not be used enough to actually produce practical quantum advantages just yet. But this is an ongoing effort, both on the device side and on the algorithm development side. So yeah, so that's my answer. Yes?
I had a follow-up, but I'll ask it
okay.
for you personally.
So are heavy atoms presenting special problems, or is it just counting the number of electrons?
Sorry, say that again.
Are heavy atoms presenting special problems, or is it just counting the number of electrons?
Do you mean, does it present special problems for the quantum computer, or do you mean special problems for AFQMC itself?
Both.
Both? So it can create special problems for AFQMC, but the actual implementation on the quantum computer will not change. So there needs to be some, and if you actually end up including heavy atoms, you need to worry about relativistic effects too. So there needs to be some modification on the AFQMC side, but the quantum computing part will stay the same.
Okay, maybe one final question by Shiwei, and then we close the session.
Thank you for the very nice talk, Junho. I wanted to understand a little bit more about the subtleties of this practical advantage. As you know well, in what you call classical AFQMC, it's not that you could not compute this overlap, but that you could not compute it deterministically with algebraic time. You could certainly sample it, which would be equivalent to what you're doing on a quantum computer. You're sampling it, right? So then to have a real practical advantage, one would have to have a much better, much more efficient sampling algorithm on the quantum computer than on a classical computer. Can you comment on that? Is that insight? Is it realized now? Is that insight? That part I don't know.
Yeah, that's a good point and good question. So it's true that if you take something like a linear combination of single Slater determinants, you can efficiently sample on the classical computer too. But if you take something like couple cluster wave function, you can't really efficiently sample anymore. If I go back to
right, with a couple cluster wave function, you could just decouple it with a Hubbard-Strong and sample it just like you do. It's
That's right. But if we're talking about formal scaling, that is exponential scaling because it involves sign problem in sampling that overlap value. So there is no tractable polynomial scaling way of computing the overlap between couple cluster wave function and arbitrary Slater determinant. As far as I know, if you know an algorithm that does it efficiently, let me know. There would be an extremely powerful method.
So, but that, I guess, so that's the part I wanted your insight on. I mean, you could, so it's not obvious that sampling the couple cluster wave function involves a sign problem that actually has an exponential scaling, right? It's not a permanent projection. It's a one-shot Hubbard-Stanovich. I was just wondering in your investigation whether you had actually done this comparison or.
I asked Sandeep's student about this comparison, so I know that the answer is correct. It has the sign problem. That's all I can say.
So it sounds like there's more to be discussed during the break. Let's thank the speakers of the session again and close the session actually. And then I'm also just passing the message by the organizers that the dinner is going to be at the same location as the lunch in 20 minutes at 6.